Hi everyone, my name is Chelsea Finn and I'm an assistant professor at Stanford, and today I'll be talking about few-shot learning in the real world. And to start off, I want to look at an example of a machine learning task and give you a little test. In particular, I'm going to give you a training set, which is these 6 data points right here, and your goal is to classify the test data point on the right based on what you can learn from these 6 examples from this training data. And in particular, these 3 examples were painted by Brock. These 3 paintings were painted by Cezanne. And now what I'm asking you is whether this painting was painted by Brock or Cezanne. Now, hopefully you can kind of figure out that this is painted by Brock. And in particular, what I think is really interesting here is humans are able to learn from just a few examples of training data to classify this problem. And in particular, if you gave this task to a machine learning system instead of a human, it probably wouldn't do very well because it was only given 6 examples of these images. So how are we able to accomplish this? Well, unlike machine learning systems, which are typically trained completely from scratch on data sets, we have previous experience. Many of you probably haven't seen this particular painting before, or maybe not even paintings from these painters before, but you know how to recognize shapes and textures and so forth, and you aren't learning from scratch. You have previous experience. And so essentially the idea behind meta learning and few-shot learning is, can we leverage previous experience in a way that allows us to very quickly learn new tasks and essentially solve like that problem that we showed before. Of course, meta learning is pretty good at few-shot image classification, but it also works well in a number of other applications as well. So we found that meta learning can allow us to train a robot to solve a new task given just a single video of a human. And you can see the resulting policy right here. And all of these objects were objects that the robot didn't see in the meta training set, and it's learning to adapt to these new objects with just a single example. Meta learning has also been used to adapt to new molecules, to essentially predict the properties of these different molecules using previous experience of looking at other molecules. We've also used meta learning to leverage previous experience in simulation to quickly adapt on a real robot to the real world, achieving a policy that can go much further with a small amount of data compared to methods like domain randomization. And lastly, it can be used, it has been used to adapt to different regions of the world, where in this example, they're looking at classifying land cover or segmenting land cover, and they have previous experience from other regions of the world, and then they want to then adapt to a new region of the world with a small amount of data. So these are just a few examples of what meta learning has successfully shown. And in general, it's a widely applicable framework and is generally shown pretty interesting and exciting results, in my opinion. But what I'd like to really focus on today is, can we actually deploy these few-shot learning algorithms into the real world? All of those were essentially kind of nice demos or showing robots in a lab environment, for example, or showing things with real data, but not actually in a live application. And what I'd like to talk about today is actually looking at these in a live application. In particular, this is the project that I'm going to talk about. The application here actually has nothing to do with computer vision, and I realize this is CVPR, but it actually uses techniques that have been very successful in computer vision and image classification. And it also illustrates general challenges that arise in real-world applications and some general ideas that we can use to try to tackle those challenges. So what is the problem? In 2020 and in 2021, Chris Peach, Mehran Sahimi, and Julie Zelensky offered this free Intro to CS course. And in 2021, it had more than 12,000 students from 150 different countries, which is, it's really an amazing course. And part of the way that they actually scaled this is they had a large number of section leaders that were helping teach. However, part of the course was also this diagnostic exam, which students would take to kind of test their own abilities for how well they were learning the material in the course. And The submissions here were open-ended Python code or snippets of open-ended Python code. And ideally, we would be able to give feedback on the students' work on this diagnostic so that they can learn and assess how well they are doing. But unfortunately, when you have this many students or this many submissions, it ends up being just a huge amount of work to give feedback on that diagnostic. And so we estimate that it would take about 8 months of human labor, and not just like really expert human labor, people who know Python well. It would take that much time to give feedback on this diagnostic to all the students. And of course, this problem isn't unique to the Code in Place course. It also arises in really any online course, and really a lot of courses in general. We spend a lot of time trying to give feedback to students that's personalized on their work. So in particular, what does feedback look like in existing massive online courses? Here's one example from, I think, Code Academy, and essentially the feedback just corresponds to these error messages, which would generally be pretty intimidating and difficult to interpret to a beginner student. Here's another example where the feedback corresponds to this standardized tooltip that provides this pre-specified message. And in general, this strategy to providing feedback tends to produce very vague feedback. And for example, here it's just telling the student that the solution is wrong and to try something different. And then lastly, another example is just to provide the solution, essentially, in like a multiple choice quiz. And really the feedback here is just limited to showing the right answer, and this doesn't really help students understand their particular underlying misconceptions. So can we provide feedback to students, and what does this challenge actually look like? So in particular, the way that we formulated this challenge is we assume that we're given some rubric, which is defined by an instructor. And the goal is to train a model that can infer the misconception on this rubric from the student solution shown on the left. So for example, they would successfully use the print function, but they didn't use a loop, and they also had a syntax error because there's a colon missing here. So we want to be able to predict, and this then kind of lends itself to a classification problem because the human is defining the rubric, and so we want to be able to predict, we want to be able to classify which misconceptions they made and which misconceptions they didn't make. Now, why is this hard? This seems like it might be straightforward. It's a classification problem, but unfortunately, grading student work takes a lot of expertise, and it's also super time consuming. And so we don't have that much data. So for example, if you even just like block-based codes, annotating 800 of them took 25 hours. And it's also a hard problem because the distribution isn't nicely balanced. There are many, many different ways to solve the same problem. And so you get these long tail distributions, and you really want to do well in the tail because that's where all the struggling students live, and that's where the feedback can be the most helpful. And then finally, people change their curriculum over time. Instructors are constantly editing their assignments and their exams. And so therefore, the student solutions and the instructor feedback are going to look a lot different from year to year. And this means that we don't have a lot of data for a single exam or for a single assignment. And then beyond those reasons for why it's challenging, naive methods also don't work. So for example, in 2014, code.org got thousands of instructors to label student solutions. And this really barely covered the distribution, and new solutions to the problem were quite frequent. And as a result, it was essentially kind of discontinued after that. And then also, if you just try to run supervised learning on the amount of data that you have for a single question on a few thousand examples, which is really at best the most data that you'll get for any question, the accuracy that you get is quite low compared to a human. Okay, so then this brings up the question of, can we use previous data from previous exams and previous questions and so forth and formulate this as a meta-learning problem? And in particular, the prior experience that we have is this 10 years of feedback from Stanford midterms and finals in the Intro CS course. And our goal is to be able to give feedback on new problems with a small amount of labeled examples, where essentially an instructor gives feedback on, say, 20 examples of the new problem, and the system gives feedback on the remaining solutions. And in particular, what does our data set look like? We took these assignments and exams, so it includes 8 final exams, 8 midterms. We also have some data from assignments. A total of 63 questions, 25,000 student solutions, and each student solution has feedback given by that rubric, like I was showing before. And every rubric is different based on the question. It's not, again, not really a single task learning problem at all. And some of the questions were also annotated by more than one TA, which allows us to compute roughly where human accuracy is. And then what do these rubrics look like? So here are some examples of rubric items, and each item has different options. And then, for example, for kind of a string insertion problem, different rubric options would be getting it perfectly, incorrectly getting a character to insert, incorrectly assuming one digit rather than inserting multiple digits, or not inserting the character at the correct place. And in particular, we can then treat every rubric option as a task in meta learning. And so therefore, every task is going to be a binary classification problem. And then from our data set, we'll get a total of 259 tasks, even though we only have around 8 exams. And so, for example, in the rubric that I was showing before, one of the tasks is to predict whether the solution is perfect or not. Another task is to predict whether or not they incorrectly inserted the right character or not, and so on and so forth. So each of these options are different tasks. And then in terms of the model, we're going to use kind of the standard support query setup where we have some support examples, which are the labeled examples that we get at analogous to the labeled examples that we get at test time. Then we also have held out query examples that test our ability to generalize to new examples of that same question and rubric. And we'll use the support set to derive a prototypical embedding, kind of following this prior work on prototypical networks, and try to classify each example in the query set by using the distance to the prototypical embedding from the binary 0 label and the binary 1 label. And so more concretely, what this looks like is we have an equation right here. For one of our query examples, we embed it using our embedding function f. We then compare it to the prototype for the label of 1, for example, or for the label of 0. We measure the distance between our embedding and that prototype using, for example, an L2 norm or a cosine distance. And then we also have some temperature term that determines how peaky the distribution should be. And this essentially tells us the prototype that we're closest to will then tell us which label we should predict. And then our loss function looks like essentially minimizing or maximizing this log of the softmax of the distances. Okay, so that's kind of the rough idea of prototypical networks and what we'll be using here. And because our inputs are a sequence of discrete tokens, such as Python code, although this is also applicable to language, then we're going to use a Roberta model, which is stack transformers, and then non-padded token embeddings are averaged into a single vector. And unfortunately, applying this out of the box doesn't work. Turns out that attention isn't all you need. And we really needed to actually develop several tricks in order to get past the fact that we don't have that much data. There are a number of tricks that we studied. I'll outline 3 of them in this talk. So the first is that we only have 259 tasks. This is not a lot. Meta learning often operates in settings where we have thousands of tasks. And so what we do is we take this idea of data augmentation, which has been super successful in machine learning more generally, and instead of augmenting data points, we augment the tasks themselves. So we're kind of bringing it up a level. And so in particular, we can generate additional tasks to train our MetaLearner on. We develop tasks, classification tasks that correspond to predicting masked tokens. And in particular, we only predict the kind of functional tokens and not things like variable names or function names. And we also predict compilation errors as tasks as well. And so with this, we can actually generate a lot more tasks and train on much more than 259 tasks, such that we can essentially learn more and essentially augment the kinds of tasks that we have in our data set. So the second trick we looked at is that if, for example, we have in the 10-shot setting or the 20-shot setting, we don't have that many examples. And so there could be actually some ambiguity in what thing we're trying to classify on. And in many settings, we actually have side information about the task. For example, the name of the rubric option or the text in the question. And so we can actually incorporate this side information into our embedding function such that we reduce the ambiguity about what the correct thing to classify is. And so, for example, we'll take the question text, compute a vector of side information, and then we'll prepend the side information as the first token in our transformer. And then we'll also do the same thing for the rubric option text as well. Okay, and then the last thing we do, which has also been quite successful in machine learning broadly, is to pre-train the model. And in particular, because this is all, we're predicting things on Python code, we try to leverage unlabeled Python datasets to help the model learn a good prior. And what we found to be most successful was this CodeBERT model, which is a self-supervised pre-training approach, which we use to initialize the embedding network. Then we fine-tune the top end layers. So the kind of architecture as at a glance is here, where we take our student code sequence as well as the question and the rubric. We pass the student code sequence through a number of transformer layers and prepend the question and rubric embeddings at each layer. And then we average to get an embedding of each solution, of each student solution. And then we average those embeddings to compute a prototype for each label within a rubric option. Then once we have these prototypes for the different labels, we can then pass in a new student code sequence and compare it to the prototype for each label to get a corresponding predicted label. Okay, so how well does this work? Before we move on to the live deployment, we looked at accuracy on held out questions and on held out exams. And first, for held out questions, we found that this method is first able to perform a lot better than a supervised baseline, just kind of supervised learning. And also we're actually surprised to find that we're also outperforming the accuracy or the average precision of a human TA on held out questions. And then when we move on to held out exams, which are even harder because we'll be encountering potentially like novel tokens much more frequently. In this case, we also found that we significantly outperform a supervised baseline, but we don't quite reach the accuracy or the average precision of a human TA. And so this suggests that there's room to grow here and room to do even better. Okay, and then lastly in these results, we did a number of ablations with a lot of the design choices that I mentioned before, including different task augmentation techniques shown in pink, different pre-processing approaches shown in this dark orange color, different pre-training, different algorithms such as prototypical networks and matching networks, and so on and so forth. And what we found here is this plot is showing the accuracy for held out rubric items and the accuracy for held out exams. And we see that these decisions actually make a pretty huge difference in the performance, where our best performance is shown up here. And in particular, everything down here is getting an accuracy of around 72.5 on held out questions, whereas over here, things are getting an accuracy of around 85%. And so this is a kind of more than 10% absolute gain in performance. Okay, so these results were pretty exciting. We didn't actually know that we're going to be able to get such good results and match the performance of a human TA. And so then we wanted to actually try to deploy this to code in place. And in particular, in 2020, they didn't actually have the bandwidth to give any feedback on the diagnostic other than giving solutions to the diagnostic. And so on May 10th of this year, the students took this diagnostic, and we then tried to give feedback on the diagnostic. And in particular, Alan Chang made this amazing UI where the students submitted their solution, and we then gave feedback using the machine learning system. And in particular, here's the feedback that's given to the student. Of course, the machine learning system only needs to classify which rubric item, and then a human enters essentially the text feedback that corresponds to each rubric item. Then the students can evaluate the feedback of whether they agree with the feedback or whether they don't agree with the feedback. The algorithm also uses attention to highlight where in the code the error comes from. And also, it's worth mentioning that things like unit tests, for example, wouldn't be successful for giving this sort of feedback because there are often syntax errors in students' code. Okay, so then we ran a blind randomized trial in the course, and it was evaluated by real students. In particular, humans gave feedback on around 1,000 of the answers, and this was used by the machine learning system to adapt to these problems. And then the machine learning model gave feedback on the remaining 15,000 solutions. And around 2,000 could be auto-graded, and so we didn't include that in the analysis. And some of the students got feedback from humans, and some of the students got feedback from the machine learning system. And what we found is, first, they agreed with human feedback around 96.7% of the time. And second, they agreed with feedback from the machine learning model 97.9% of the time. So not only did the machine learning model actually match the performance of human feedback, but it also actually exceeded the performance in a significant way, although with a relatively small effect size. So kind of overall, humans gave great feedback, and the machine learning model gave even slightly better feedback than that. And without this sort of machine learning system, we wouldn't have been able to give feedback to these 15,000 solutions. And then lastly, while this measures agreement, whether or not this feedback is actually useful is also important. It might be right, but not actually be useful. And overall, we asked the students how useful they thought it was, and overall, they gave it a rating of 4.6 out of 5. So overall, they found it to be quite useful as well, which is a really great sign. Okay, then the last thing that's really important to look at here is if there's any signs of bias in the system. And so we looked at the how well the system performed on some of the larger demographic groups where we could get significant results. And we found that for the largest gender groups in the largest countries, we didn't really see any signs of bias in terms of looking at the agreement between students from those different demographics. And so this was our initial look at whether there's bias in the system, and this seems really encouraging about lack of any bias. However, we're doing kind of a more detailed analysis now on this as well. Okay, so overall, I found this work really exciting because I think it's, well, first on the education side, it's the first successful deployment of machine learning driven feedback to open-ended student work that's provided in an automatic way. And it really significantly improves upon the kinds of feedback that we can give automatically by using prior approaches. And further, on the machine learning side, it's also, to my knowledge at least, the first successful deployment of few-shot learning methods like prototypical networks in a live application. And then I guess more broadly and potentially most importantly, I think that this is an example where the value added by the machine learning system was very, very clear. It was a setting where we wouldn't be able to give feedback to these students otherwise. And also it's a setting where the machine learning system worked closely together with humans to provide the best feedback. So like I mentioned before, a human is the one that kind of provided this feedback text for different rubric items, and then the machine learning system is what predicted the rubric item. And I think that in general, education is a really hard, really challenging application. And we need to actually build systems that can work together with humans to actually really give the best experience to students. And like, by no means like these sorts of systems, I don't think they're at all capable of replacing teachers. It's really the ability to actually augment teachers and provide a better experience to students. And that's what I think is really the most promising about this application, or what's most promising about this direction of research. Okay, so with that, I'd like to thank everyone involved in this project, especially Mike and Chris, who did a ton of work to actually make this happen and actually get this out in the real world. And also, if you're interested in learning more about meta learning, I'd encourage you to take a look at the course materials in my course. All the lecture videos are available online.